2 billion tons of waste are generated annually across the globe, and more than 20% of this volume consists of glass. Millions of glass bottles sit in landfills for over 1 million years without undergoing any natural decomposition, which creates an unmanageable accumulation of refuse. Why is this material specifically targeted for large-scale industrial recovery? At first glance, the sheer volume of discarded containers seems like a permanent environmental burden, but in reality, glass possesses a unique molecular structure that allows it to be recycled indefinitely without compromising its quality or structural integrity. The process is only gaining momentum. One can notice how hundreds of tons of broken and contaminated glass fragments enter the facility daily to be returned to the production cycle. How does the transformation of these messy, jagged shards into clean and shiny bottles actually occur? The journey involves a series of complex mechanical and optical separations. It is visible how the equipment gradually removes labels, plastic caps, and metallic rings from the incoming stream of raw material. Everything only gets more complicated at the next stage of purification. Automated systems sort the material by color and chemical composition with high-speed precision. Laser sensors and air jets work in tandem to deflect impurities from the main conveyor belt as it moves. The equipment operates ceaselessly to ensure that only the purest cullet reaches the melting furnaces. And this is not the limit for the technical accuracy required in such a massive industrial operation. Large piles of sorted glass are eventually fed into high-temperature chambers for complete liquefaction. The material is heated until it reaches a molten state, allowing it to be molded into entirely new containers. The process concludes this phase, opening the road to formation as the liquid glass moves toward the casting machines. 10 to 20 cents is the typical refund value assigned to a single empty glass bottle within a circular economy. Why is such a small financial incentive used to drive a massive industrial process? While household waste often contains a chaotic mix of materials that makes automated sorting expensive and technologically complex, many European countries have integrated glass return machines directly into the urban landscape. This system transforms what would be common trash into a valuable asset the moment the consumer finishes their beverage. The equipment works with calculated efficiency. One can notice how the reverse vending machine scans each unit before sorting it into internal storage. Because the glass is collected separately from regular waste, factories receive a stream of raw material that is already pre-sorted and consistently clean. This approach motivates the public to act as the primary sorters, ensuring that the supply chain remains steady and reliable for the recycling plant. It gets more complex further on. Specialized trucks arrive at the collection points once the internal storage bins reach full capacity. It seems like a simple logistics task, but in reality, the coordination of these pickups prevents the entire urban recycling network from stalling. Forklifts lift large plastic bins containing thousands of empty bottles onto the transport beds. A single full-size truck can carry between 20,000 and 30,000 bottles in a single trip, which translates to approximately 10 to 12 tons of material. The equipment gradually fills the transport space as the driver secures the cargo for transit. The process is only gaining momentum. The vehicles move from supermarkets and city collection hubs directly toward the centralized recycling facility. One can notice the sheer volume of glass packed tightly into the bins as the truck maneuvers through traffic. But this is just the beginning of the material's physical transformation. Drivers back their vehicles into massive industrial storage bays upon arrival at the plant. The hydraulic systems engage and the load is released in a controlled cascade. Tens of thousands of bottles tumble down into the bay, creating a sharp clatter that echoes through the facility. Mountains of colorful glass quickly fill the floor space, reaching heights of several meters in just a few minutes. It is visible how the clear, green, and brown bottles sparkle under the overhead industrial lighting as they form distinct piles. The material is now concentrated in one location and is ready to enter the next stage of the manufacturing cycle. The bottles lie in sorted heaps, awaiting the transition to the crushing and melting phase. Thus, the glass reaches the standard ready for the further stage. 80% is the approximate level of purity reached by the glass stream after its initial mechanical and magnetic separation phases. Why is such meticulous cleaning required before the glass even reaches the melting furnace? At first glance, the piles of discarded shards look like simple waste, but in reality, they are the vital feedstock for an entire industrial recycling chain. Without removing every fragment of metal, paper, and plastic, the final glass product would be structurally compromised and visually flawed. Massive loaders with reinforced steel buckets drive toward the towering mounds of raw material. One can notice how the hydraulic booms tilt slowly as the machines scoop up thousands of pounds of glass in a single motion. The loaders navigate the yard and dump their cargo into the plant's feed hopper with a thunderous crash that echoes through the facility. A cascade of sharp shards slides down the steel chute, landing on a conveyor belt that begins its constant rhythmic movement. The equipment gradually carries the mixture of glass, dirt, and sand deep into the facility for its first technical treatment. Powerful motors drive the vibrating screen, which shakes the material with high-frequency oscillations to sift out grit and fine dust particles. The process is only gaining momentum. It is visible how the glass emerges from the screen significantly cleaner, though larger contaminants still remain hidden within the stream. Technical staff stand positioned along the moving belt to perform a manual inspection of the material flow. Workers carefully extract pieces of plastic, large paper fragments, and other debris that automated sensors might overlook at this early stage. This combination of mechanical vibrating force and human precision results in a batch that is prepared for the next level of purification. But this is just the beginning of the separation process. Why are metallic bottle caps not a permanent problem for the purity of the glass? The answer lies in the physics of induction and magnetism. A high-powered magnetic separator is suspended over the conveyor, creating a concentrated field that reacts with the steel caps. One can notice how the metal bits are pulled upward and away, while the non-magnetic glass continues moving forward undisturbed. The glass is now much closer to its final transformation, but the fragments are still too large for efficient melting. The larger pieces enter the primary hammer mill, a massive industrial unit equipped with high-speed rotating steel hammers. These hammers smash the shards repeatedly until they are reduced to uniform fragments known as cullet. It looks superficially simple to break glass, but the machine must ensure a specific particle size for the entire stream. Automated sensors detect any stragglers that remain larger than the required specification and divert them back into the mill for a second pass. This ensures that the resulting cullet looks almost like man-made sand, consisting of fine, sparkling particles. Because the surface area is increased by this grinding, the cullet melts significantly faster in the furnace. This technical advantage allows the plant to save up to 40% of the energy compared to processing raw limestone or sand. Everything only gets more complicated as the glass moves toward the final cleaning stages. A powerful suction system generates a focused stream of air that blasts through the falling cullet. This airflow strips away remaining label fragments and lightweight adhesives, blowing them into a separate collection zone. Transition to the next level occurs as the purified material enters the optical sorting chamber. The optical sorting system represents the most precise technical step in the entire production sequence. One can notice the glass cascading down like a shimmering waterfall past a bank of high-speed laser sensors. These sensors scan every individual fragment to identify its specific color and chemical composition. Tens of thousands of pieces are processed every single minute with incredible mechanical speed. The moment a stray ceramic shard or a piece of brown glass is identified within a clear stream, the system fires a precise puff of compressed air. This air blast shoots the unintended particle into a separate channel with millisecond timing. Even the slightest mixture of different shades would ruin the quality of the final recycled batch, making this accuracy essential. The sorted glass particles then move along the final conveyor toward dedicated storage zones. The tiny fragments are directed into separate areas divided strictly by their color profiles. They gradually accumulate into massive stockpiles, forming organized mounds of raw material ready for the final heat treatment. From here, the sorted cullet is prepared to be transformed into brand new glass containers. The material is ready to move to the next processing phase without haste. 20% to 70% of the total batch weight consists of recycled cullet, as the sorted and ground material cannot enter the furnace in isolation. Why is this ratio so critical for the efficiency of the facility? At first glance, the process seems like a simple fusion of old and new materials, but in reality, the cullet acts as a thermal catalyst. Without this specific concentration, the melting phase would require significantly more time and fuel to reach a liquid state. Pure silica sand forms the primary foundation of the mixture to ensure the final glass achieves absolute clarity. The equipment gradually introduces soda ash, technically known as sodium carbonate, into the blend. This specific additive performs the vital function of lowering the melting point of the silica, which reduces the total energy expenditure of the entire operation. One can notice how limestone is integrated into the batch as well. This mineral provides the necessary structural integrity and chemical stability required for the glass once it undergoes solidification. Manufacturers often incorporate secondary minerals such as dolomite or alumina to refine the physical properties of the glass. The process is only gaining momentum as metal oxides are measured and added to precisely calibrate the final color. It is visible how the components are layered before entering the mixing chambers. Transition to the next level. 10% increases in cullet volume yield a 3% reduction in total energy consumption, while simultaneously decreasing carbon dioxide emissions. The use of recycled glass allows the melt to flow with greater fluidity, cutting energy requirements by up to 40% compared to batches composed entirely of virgin raw materials. Standardized factory formulas dictate the exact proportions of every grain. Because a lack of homogeneity would result in structural flaws, the internal blades of the mixers rotate ceaselessly until the blend is perfectly uniform. 1,250 degrees Celsius is the temperature inside the massive gas-fired furnace where the mixture is eventually fed. This heat exceeds the thermal intensity of volcanic lava and triggers the primary chemical transformation. Everything only gets more complicated as the transition from solid to liquid begins. Technicians, shielded by fireproof suits and heavy protective gloves, monitor the flow of the material as it moves into specialized crucibles. Ambient temperatures inside the facility reach nearly 3,000 degrees, creating an environment that is physically difficult to endure without specialized gear. Each crucible mouth is sealed shut once the ingredients have stabilized to prevent heat loss. This containment ensures that the internal thermal environment remains consistent throughout the duration of the melt. But this is just the beginning of the thermal cycle. 24 hours of constant heating transforms the grainy sand into a thick, viscous substance. The camera glides along the furnace floor where a brilliant glow indicates the presence of the liquid glass. It appears as a dense and shining mass that has achieved the specific viscosity required for shaping. It gets more complex further on. 5 hours of additional heating follow to allow all trapped gases to rise and escape the surface of the melt. One can notice the absence of bubbles as the glass reaches a state of high purity. The material maintains its molten state during this period to ensure the final product is free of internal imperfections. Molten glass eventually leaves the static chamber and flows directly into a spinner. Thus, the material reaches the precise state ready for the next phase of the production chain. Thousands of tiny holes in the rotating spinner serve as the exit point for molten glass, which is transformed into ultra-fine fibers at extremely high speeds. Why is the rotation speed of the spinner kept at such a high frequency? Centrifugal force must be sufficient to eject the liquid material with enough energy to maintain a consistent fiber diameter. The glass shoots out through the apertures, immediately encountering a powerful stream of hot air that blows downward to stretch the filaments into their final thin form. Compressed air assists this process by controlling the length of the fibers and providing initial cooling to the structural strands. One can notice how the first spray ring applies a fine mist of water to lower the temperature of the material rapidly. It gets more complex further on. A second ring coats the cooling fibers with an exclusive formaldehyde-free formula known as the biobinder, which remains completely colorless during the application phase. The fibers are gathered within a specialized forming chamber and deposited onto a moving conveyor belt to create a continuous rock wool mat. At first glance, the distribution of fibers might seem random, but in reality, a cross-distribution system moves back and forth with mechanical precision. This ensures that the density of the material is uniform across the entire surface of the conveyor. Freshly spun fiberglass appears naturally off-white, characterized by a light and fluffy texture as it moves along the line. The liquid binder is sprayed onto the surface, remaining clear so that the mat retains its initial white color for the time being. But this is just the beginning. The material enters a hot curing oven where the binder undergoes a chemical transformation, hardening and changing hue to yellow, orange, or pink depending on the specific formula used. It is visible how the fiberglass wool passes under heavy rollers that compress the soft, airy mat into a firm block of consistent thickness. This mechanical compression locks the fibers together, creating a stable structure that is far easier to manipulate during the subsequent stages of production. The compact block advances into the cutting line where sharp, high-speed blades slice the material into panels of precise dimensions. Sensors and mechanical guides monitor the movement of the block to ensure every sheet meets exact building standards. Following the cutting process, the panels are wrapped in a protective film that is tightly sealed to prevent moisture infiltration and physical damage. Forklifts lift the finished bundles onto wooden pallets, stacking them for transport across the country. In the United States, the pink fiberglass insulation produced by Owens Corning occupies the majority of the market share. The company successfully trademarked the specific pink color of their product, establishing it as a legally protected signature of their brand. The finished material is loaded onto trucks, concluding its journey from the furnace to the construction site. 1,400 degrees is the maximum temperature that the molds made of cast iron or alloy steel can endure without deformation. Because glass requires a physical constraint to take on a specific geometry, the creation of these specialized containers is the mandatory next step in the manufacturing cycle. Engineers utilize advanced computer-aided design software to calculate every dimension, thickness, and line with high precision to satisfy rigorous technical standards. Why is such a high level of digital accuracy necessary before any metal is cast? The digital blueprint dictates how the molten material will flow, and any error in the design phase would result in structural failure during mass production. Once the molds are manufactured from these durable alloys, they are prepared to receive the liquid glass and shape it from the internal cavity outward. Everything only gets more complicated. Specialized technicians install the completed molds into the double blow production line, a system recognized as one of the most reliable methods for manufacturing hollow glass products like food jars, pharmaceutical containers, and soft drink bottles. It is visible how the forming process begins with the release of molten glass segments known as gobs into the initial blank mold. These gobs are severed from a continuous liquid stream at temperatures of approximately 1,100 degrees, a thermal state that ensures the perfect viscosity for smooth and consistent shaping. One can notice how a jet of compressed air is blown in from the top of the blank mold, forcing the hot glass against the inner walls. At first glance, the resulting shape seems finished, but in reality, it is only a parison, which is a hollow, bubble-like structure featuring a narrow neck. The process is only gaining momentum. Still radiating an intense heat, the parison is transferred by mechanical arms to the final mold located only a few inches away on the same line. In this second stage, another burst of compressed air is injected directly into the center of the parison, stretching the softened material until it presses tightly against every contour of the mold cavity. In just a few seconds, the full geometry of the bottle is established. It only looks obvious and effortless from the outside, but in reality, every valve and sensor is synchronized to 1/1000th of a second. This extreme level of precision control makes it possible to manufacture hundreds of thousands of identical units every 24 hours. The equipment gradually moves the hot glass into the next phase. One can notice the glass bottles as they emerge from the molds, radiating a deep red heat that makes their surfaces shimmer like glowing metal rods in the dim light of the factory. Robotic arms move with programmed precision, gliding into place to engage with the freshly formed containers. Each bottle is lifted with mechanical care and placed onto the moving conveyor belt. The entire scene unfolds with a lack of noise and a total absence of haste, as the automated systems maintain a perfect rhythm. The molten stream of material has now taken its physical form, and the glass begins its slow cooling process on the way to the final inspection. 450 millimeters per second is the average speed at which the conveyor belt guides the newly formed glass containers. The bases of these bottles still glow with an intense orange heat as they approach the cooling zone. They enter a long yellow tunnel where the internal atmosphere is strictly controlled to allow the temperature to lower little by little. This gradual reduction in heat provides the glass structure the necessary time to settle into a stable state without the risk of thermal shock or immediate breaking. Why must this cooling stage be conducted with such calculated slowness? At first glance, the process seems like a simple delay in the production chain, but in reality, if the glass cools too rapidly, internal stresses will cause the bottle to shatter instantly. This thermal treatment stage takes its time, often lasting several minutes and sometimes stretching to 40 or 50 minutes depending on the thickness of the glass wall. The process is only gaining momentum. Once the cooled glass bottles exit the tunnel, they reach a high-precision inspection station. Here, an array of optical sensors and high-speed cameras examines each unit in real time as the equipment moves with rhythmic mechanical clicks. Every microscopic detail is checked. The moment a defect appears, whether it is a crack, a gas bubble, a surface scratch, or even a tiny structural warp, the automated system flags the item. Pneumatic injectors immediately pull the flawed bottle off the production line. One can notice how the rejected glass is diverted into a separate chute for remelting. It gets more complex further on. The next stage focuses on a close examination of the bottle mouth and sealing surface. An automated manipulator rotates each bottle with precision, while optical sensors and mechanical probes work in unison to detect any deviation. Whether the system identifies a chipped edge, a hairline crack, or a variation in dimension of only a few millimeters, the bottle is discarded. Only containers that pass this strict mechanical check are allowed to move forward. Transition to the next level. After clearing all inspections, the glass bottles are carried to the palletizing section, where heavy robotic systems take charge of the workflow. These machines are designed for high accuracy and absolute absolute uniformity, organizing thousands of individual bottles into dense blocks with ease. One can notice the clamp mechanism equipped with suction cups as it lowers with the hiss of hydraulics. The robotic arm grips a full row of glass and sets it carefully onto the pallet layer. To protect against impact during future handling and shipping, the machine places a protective sheet between every horizontal layer. When the stack reaches its final height, an automated wrapper secures the entire pallet in a tight layer of polymer film. Everything only gets more complicated as the system generates a unique identification tag. This code corresponds exactly to the production batch and the time of manufacture. Finally, the glass pallets are moved into the storage zone, where they are neatly stacked by forklifts and made ready for shipment. From this point, the containers travel across the globe to be filled and distributed into the consumer market. The rebirth cycle of glass reaches its technical conclusion. Glass recycling serves as a physical example of how modern industrial technology transforms waste back into a primary resource. The material returns to the production loop, maintaining its properties through an infinite number of cycles. Thus, the glass reaches a state where it is ready to begin its functional life again as a finished product.